All right. Good morning, everyone. I think this is where we left off last time, looking at what the telescope, the newly invented telescope, that new technology could do to foster the environment of the scientific revolution. We saw the measurement of Mars leading to an great expansion of the distance to the sun, getting about 90% accurate for a modern value. And here we'll see the first measurement of the speed of light. And not surprisingly, given the fact it's so fast, that the first measurement comes from an astronomer, that you would need that kind of vast distances. So let me get started with that. Ole Roma, a student of Cassini there in Paris, who we saw last time, he was studying the motion of Io, one of the moons going around Jupiter. And of course, the assumption is Io is going to go around in a periodic time. It's not going to be varying in how long it takes to go around from one orbit to another. But he noticed a strange thing as he measured the appearance of Io coming from around Jupiter, so that we could finally see it and how long it stayed visible until it disappeared behind Jupiter again. As you looked at the times it took for Io to appear and then to appear again after it made its full revolution, the times were not constant at all. They varied. They varied back and forth within a range, but they were definitely varying, with the greatest variation altogether being about 22 minutes. And he thought about this and said, what clearly it's not Io that's doing this. Io is going around according to all expectations of all the motions of the planets going back thousands of years, would be a regular motion. What would be causing this variation? And finally, what he realized what it was, of course, was us moving around the sun. So we'll take a look at an animation of this. Here we have the Earth going around the sun, and here we have Jupiter with Io going around Jupiter. And here is the line of sight when Io finally comes around Jupiter so that we could see it. This would be the line of sight. And we would see Io for as long as it's in front of Jupiter, and then it would disappear behind it, like this. And then it disappears for a while. And when it appears again, the Earth is no longer where it was, it's in a different place. And again, disappears. And when it appears again, we are in a different place. And this is what Roma realized, what he was seeing. He was seeing the fact that it took light a longer and longer, or a shorter and shorter time, as the orbit of the Earth gets around the sun and we start to approach Jupiter. Then it would take a shorter amount of distance for the light from Io to reach us as we got closer and closer to Jupiter. And of course, the motion of Jupiter is relatively slow compared to the Earth. It takes 12 years for Jupiter to go around the sun. So just for one particular revolution of the Earth, you're only talking about a relatively small change in distance of Jupiter itself. And so this is what Roma realized he was looking at. Okay, he was literally looking at the Earth approaching and moving away from Jupiter, and therefore from the light coming from Io. And he was able to measure that. Like I say, the biggest measurement was 22 minutes. And so he did a simple calculation. So that he didn't do the calculation. It was Huygens who did the calculation. He'll come up in a minute. But the calculation is pretty simple. To measure speed, it's distance over time. And so the total distance that this 22 minutes was looking at was pretty much the total diameter of the motion of the Earth. So it will be Earth's diameter over 22 minutes, distance over time, and you simply put in the numbers. We have Cassini's number of the radius of the Earth from the sun. So the diameter will be twice as much, and dividing by 22 minutes times 60 seconds per minute. And you do the arithmetic and you get a fantastically high number. Right? You get 132,000 miles per second, And this is in fact 70% of the modern value. The number that we all should know, 186,000 miles per second, is the speed of light. If you were to turn that into miles per hour, you would get 475 million miles per hour is what he calculated. So you can see the numbers here are just jaw-dropping, like the numbers that modern astronomy and modern physics gives us. These are the equivalent kind of jaw-dropping numbers. We talked about the speed of the Earth going around the sun at 66,000 miles per hour. This is 475 million miles per hour. Is the speed of light. Okay, it is just beyond anything. But certainly, it's beyond anything we can imagine today. The speed of light is something that we don't have any kind of visceral understanding of. Maybe the best token of that would be that it takes the light from the sun 8 minutes to get here. The light that we see in the sun is 8 minutes old. When you see the sun setting down in the ocean, what you're seeing is the sun 8 minutes ago. It's already been down for 8 minutes. That's how long the light takes to reach us. So a very impressive example of the measurement. Here is Huygens, and here is his some of his resume, a couple of highlights. He designed the micrometer mechanism for the mounted telescope. Talking about the telescope getting more and more accurate. This was a major development of being able to move the telescope very, very slightly to measure those tiny changes in sweep of arc. We're not measuring in degrees here. We're not measuring in minutes. This mechanism allowed us to measure things in arc seconds. He was the inventor of the pendulum clock, a very important piece of technology where we could begin to measure time much more accurately. A far cry from Galileo having to sing melodies and seeing where things stopped in his experiment in the place on the melody, or a water clock. And finally, of course, his measurement, his development of the wave theory of light. We, of course, have no time for any of this, unfortunately. We could spend a couple of classes on Huygens. He's the second greatest scientist of his era. As has often been said, he would have been the greatest. He just had the unfortunate luck of being born and living in the time of Newton. And one last piece of technology that the telescope gives us, Flamsteed, the first Royal Royale, a friend of Newton's, as the telescope became more and more accurate, he was able to measure the actual apparent disk size of the planets. Most interesting when they were the closest in opposition. Let's take the one that we were familiar with from Cassini of Mars. He was able to measure the actual angular size of Mars at opposition at 32 arc minutes. I remind you, 1 arc minute is 1/60th of a, I'm sorry, 1 arc second is 1/60th of a minute, which is 1/60th of a degree. This is a tiny, tiny angle in the sky. Not a bad number. The modern number is 24 arc seconds. But given the fact that Cassini tells us how far away Mars is in opposition, and now that Flamsteed has measured this angle P, the vertex angle, we again have an isosceles triangle, knowing the vertex angle now, and one of the sides, certainly some trigonometry can tell us what the base of that triangle would be. But that base is actually the diameter of Mars. He calculated a number of 5,000 some odd miles, which is about 69% of the size of the Earth, and the modern value is 53%. Again, accurate enough for the first attempt at this kind of thing. What the telescope is doing, guys, it is not only expanding the size of the universe, and as, for example, the distance out to the sun getting further and further away. In another way, it's drawing the heavens in by making these planets real. They're real bodies like ours. They're becoming real to us just as the moon has been real for a long, long time. And of course, Galileo with the Starry Messenger made it very real with the mountains and the provinces and the seas and everything else. But now even the planets are becoming real. They're no longer these points of light, no longer this little blob of ether being carried around by a big blob of ether, but they're worlds in themselves. Okay? And we have the speculation of maybe there's people or life, intelligent life, whatever, on these planets. All these become valid speculations, and they become more understandable by looking at these kinds of developments and learning these kinds of things. And finally, we want to talk about Descartes, certainly the most influential philosopher of the scientific revolution, one of the most influential philosophers of all time, considered the father of modern philosophy. First thing I want to remind you of, he is the co-inventor of analytic geometry with Pierre Fermat, of Fermat's last theorem fame. And the development or the invention, depending on your philosophy of mathematics, of analytic geometry is truly the beginning of modern mathematics. There is no calculus without analytic geometry, and without calculus, there is no mathematics as we would understand it today. So he was, in fact, a great mathematician, among other things. What he wanted to be was a great philosopher. And he is, of course, very important, very influential. We remember our philosophy 101 with the Cartesian skepticism of I think, therefore I am, and the rationalism, and of course the dualism, the mind-body problem, and all the rest. For us, where we want to focus on Descartes' thinking is his theory of the world. Descartes was very ambitious. What he wanted to do was he wanted to develop an entire philosophical system that explained everything. No one had attempted this until the times of Aristotle. Descartes thought it was time again to give it another shot, giving all the things that we've learned since Aristotle's time. And one of the important ideas that he shares with Galileo, that in both their writings, both in Galileo's writings and in Descartes' writings, is the idea of materialism, that the only thing that makes up the world really are physical objects, matter. Okay? They ask the question, what is truly fundamental behind everything in the world, behind all the behavior that we see, everything that we can learn? What is truly, truly fundamental? In the classic paradigm, it was qualities like heaviness and wetness, natural places and violent motion, causes and purposes. These were the fundamental things that you had to deal with in your natural philosophy if you wanted to get to the very bottom of why things are the way they are. Galileo and Descartes said, no, it's something actually much simpler than that, something much more obvious and much more fundamental, obvious at least to them. And it was matter taking up space, whatever their shapes and weight were, but it was fundamentally was matter and how they move, how matter moves, and therefore how matter interacts with other matter as they move together with their interaction. That's what's fundamental. That will explain everything. It is fundamentally matter and its motion. The one exception both of them made as good Catholics was the human soul. The human soul was not matter. It was of a different kind of substance, and let that stay the way it is. But if you want to turn your attention to natural philosophy and explaining the physical world, then what you have to deal with, and with the only thing you have to deal with in finding ultimate explanations, is the matter that is composed of and how that matter moves. And this is the doctrine of materialism, where the only thing in the universe is matter. There are no more spirits. Those are gone from the universe. There's no, all we have is physical, corporeal matter. And all the other physical perceptions and sensations that we have of color and taste and smell and etc., hardness and all of those things is nothing more than matter impressing upon our senses with its motion. As it moves towards our senses, as it bangs into our senses, literally, that's literally what they're talking about. As matter pushes in and interacts physically with our senses because of its motion, that's what brings all these sensations that our brain somehow or other can interpret. That's what is truly fundamental. Galileo says, if ears, tongues, and noses were removed, I am of the opinion that shape, size, and motion would remain, and there would be an end to smells and tastes and sounds. Descartes' famous expression was, give me extension and motion, and I will construct the universe. So they replace these qualities with, in fact, measurable quantities: distance, time, temperature, and weight, pressure. And all these things come from either a result of or measurements of matter in motion. So here's our first great contribution in terms of natural philosophy of Galileo and Descartes, leading to clearly a paradigm shift away from that classical Christian paradigm of the late Middle Ages. The second paradigm shift, this is mostly can be attributed to Descartes, is the mechanical universe, the mechanical philosophy. Again, Descartes asks, what is the fundamental causes of the behavior that we see? Yes, we know it's matter in motion, but what, the classical paradigm, the fundamental causes was the purpose that things were able to fulfill. That was the fundamental explanation of things. For example, what was natural motion? Why did things move naturally? Because they wanted to go to their natural place. That was the purpose of things, and that's what created the motions that we see in the heavens and things falling naturally, free fall, etc., etc. Descartes said, no, all observable processes and phenomena are caused by the physical motion and therefore the resulting interaction of microscopic elements of matter. Really just taking the next step forward from materialism to the true mechanical universe. Mathematics, of course, is essential. He was a mathematician. Mathematics is an essential component of science. It serves as a tool to describe and analyze motion, but it is not the ultimate explanation. It is not the ultimate description. The ultimate description is in the motion of matter and how matter interacts with each other. That's the ultimate cause of things. If we want to find the true science of things, we need to look at that direction. We can't stop at the mathematics. That's merely a description, and a very helpful description, and it can help us analyze the true causes of things, which is the interaction of matter with itself through its motion. Very fruitful idea. Descartes virtually built all of his philosophy on this idea. He explained the formation of the world and the motion of the planets around the sun using this idea. We'll come to that in the next slide. But we have to admit that this is a very powerful idea, the idea of motion, bringing all of the physical world to understanding. Heat, for example, in the 18th century was considered the motion of a fluid, caloric. In the 19th century, it becomes the motion of molecules. Light and sound, they were waves of vibration. A medium was vibrating up and down or back and forth. Motion is what causes light and sound. Electricity in the 18th and 19th century was explained by a motion, again, of a fluid, and the excess or the deficit of that amount of fluid would create positive and negative charges. So this idea of moving fluid explained electricity for a long time until it was overturned by the motion of the newly discovered electrons. So yes, motion is very much what physical science still today is about. What is moving now has changed. Hopefully we'll get a chance to look at that a little bit at the end of our class, but we can see the impressive idea of motion here. And that's what Descartes says, that this is what you have to focus on, nothing else. Okay? This is what causes what we see, nothing else. There are no miracles. There are no things that nature can do that's beyond what can be explained by matter in motion. Those other things do not exist, cannot exist. This is where we find all of our explanations. We want to come to study a phenomenon. This is your direction. This is the framework that you work in. These are the experiments that you design, et cetera, et cetera. And like I say, he did try to have a total comprehensive philosophy of everything, basically. And when it came to natural philosophy, he, of course, turned to his idea of matter and motion. And he has this theory of vortices, these swirling cyclone kinds of motions of matter cycling around, banging into each other, literally banging into each other to cause changes in motion. And this was his explanation, for example, for the planets moving around the sun. This was even his explanation of gravity. Somehow or other, there are vortices surrounding us and banging on our head, banging on our shoulders, and pushing us down to the earth. Literally, this was, it sounds a little crazy, but, and this was very, very influential ideas, this fundamental idea, not so much in the details, but this fundamental explanation was very satisfactory for a long, long time. Interesting about this whole thing that I just described, particularly the vortices and everything, it was completely devoid of mathematics. For the inventor of analytic geometry, for clearly a very talented mathematician, he had no mathematics in his overall natural philosophy. And of course, this whole business of vortices is all wrong. We'll see that Newton in the Principia completely destroys this idea. And there's no way that anything like this theory of swirling vortices could possibly explain the motion of the heavens at all. So this really does just remain kind of a metaphysical explanation. But again, it had a very influence for a long, long time, particularly on the continent, particularly in France and Germany and Italy, those philosophers, not so much on the English side because of the influence ultimately of Newton. So all physical processes of nature can be explained by matter in motion and their context. And this is called the mechanical philosophy of nature. For what has already been said, we have established that all bodies in the universe are composed of one and the same matter, which is divisible into indefinitely many parts. It's interesting. Galileo was an atomist. He believed in atoms like the old atom theory of the Greeks. Descartes not. Descartes believed in the continuous nature of matter. The age-old question, is matter like a bucket of sand or a bucket of molasses? And of course, we have come to understand the reality of atoms, that matter is ultimately a bucket of sand. But Descartes was actually in the school with Aristotle, that no, it was more like a bucket of molasses. You had to analyze that bucket by looking at small pieces of molasses, but you could indefinitely cut this again and again down to infinity. So in fact, divided into a large number of parts which move in different directions and have a sort of circular motion. Moreover, the same quantity of motion is always preserved. He was groping towards a conservation of energy, a conservation of momentum, that the total amount of motion in the universe was always the same, and it just kind of moved around in different places as things banged around, kind of groping towards this idea of the conservation of momentum and energy. Okay, that's where things stand in the generation before the time of Newton. As I change slides, any questions or comments about that? You have to unmute yourself. You guys have been awful quiet the last two classes. I hope I hope I have not gone beyond your comfort level of what we're talking about. No thoughts, no questions before we proceed. Okay, we're going to quickly go through Newton. Unfortunately, an occupational hazard of all teachers is they never have as much time as they would like. So we want to focus on the ideas that Newton brings to the table as opposed to his life and other kind of narrative things, which you can easily read in the slides. But we start with this slide, which I think is important. What are the two great outstanding problems of Newton's time? And clearly they were, what are the forces that act upon the planets to explain Kepler's three laws? Right? We have this new model of the universe, incredibly accurate, getting just more and more accurate, more and more impressive with the telescopic measurements, clearly in the scientific community by the time of Newton, very much the astronomers at least have moved and understand the importance of Kepler's work, even though they still might not understand it. They understand its importance and the accuracy of his models. So what explains these three strange laws, and the fact that they seem to be independent of each other? And The explanation that Kepler tried with the magnetism and all that stuff clearly was completely inadequate. And again, Kepler, being a very, very talented mathematician, a very powerful mathematician, was not able to create a mathematical explanation for his mathematical laws. He just did not have the math to do it. He was just didn't have what Newton had to invent in order to do it. And the second great question is, now that the Aristotelian theory of terrestrial motion is gone, is rejected, how do we build on the work of Galileo to make a comprehensive theory of motion that can explain everything from the parabolic trajectories of projectiles all the way to the elliptical orbits of satellites and everything else in between? Satellites, by the way, is a word coined by Kepler, and it means any body moving around some other large central body. So the moon is a satellite, the Earth is a satellite, and it turns out we'll see that the comets are satellites, etc., and our artificial satellites of today are GPS satellites, a word coined by Kepler. Newton, in his Principia, sums up the game, what has to be done. He makes it sound very easy. For the whole burden of philosophy seems to consist of this: to derive 2 or 3 general principles of motion from the phenomenon, from experiment, and afterwards to tell us how the properties and actions of all corporeal things follow from these manifest principles. Sounds simple. First of all, you have to find these general principles, and then you have to go ahead and show how everything else follows from them. That's the hard part, I guess, is that thing. So again, Newton's life we will not spend any time on, but here in his work in Shelter in Place, when the Great Plague came and the university was closed and everyone was sent home, he spent 2 years back on the farm of his mom. And what did he do? Very interesting, given the fact that we were sheltered in place for at least a year, if not more. He studied, of course, all the great works that he could get his hands on. He read, we know he read Descartes, Galileo, Kepler, all the rest. And what he did was he mastered the mathematics of his day all on his own and developed not only the binomial theorem, but the beginning of the calculus. He formulated the laws of motion, which we'll look at in detail in a moment. He developed the law of gravitation, okay, looking at Kepler's laws, finally understanding the importance of Kepler's laws and what it was truly saying, and investigated light and the theory of color, as we know. He wrote many years later, he said, in that same year, when he was 22 years old, I began to think of gravity extending to the orb of the moon. And from Kepler's rule of the periodic times of the planets, that's the third law, I deduced that the forces that keep the planets in their orbs must be reciprocal as the squares of their distance, that is, inversely proportional to distance, 1 over distance squared, about which they revolve, and thereby compare the force requisite to keep the moon in her orbit with the force of gravity on the surface of the Earth. Okay? He compared those 2 forces and what would be the relationship between them, and could he deduce from that some kind of a mathematical rule of how force changed going from the surface of the Earth up to the distance of the moon. And found them to answer pretty nearly that his hypothesis, which we'll look at in a moment, answered pretty nearly. And we'll see what he means by that in a moment. All this was in the 2 plague years of 1665 and 66. For in those days, I was in the prime of my age of invention and minded mathematics and natural philosophy more than at any time since. So he's claiming that he spent those 2 years on the farm, spent more time doing physics than any time afterwards. And here is the famous experiments of light, breaking up white light into its colors of the rainbow, and then bringing it back into white light, showing that white light is in fact the composition of the colors. His time as university professor, what I've outlined here, highlighted here, is his invention of the reflecting telescope. Yeah, just as Kepler gave us a new design for the refractor. There was, again, bouncing around the idea of making a telescope out of mirrors. Newton was the first one to actually make one, actually look at the theory and create a telescope. He was very good with his hands, as Galileo was. He proposed a particle theory of light, as opposed to Huygens's wave theory of light. And of course, in 1687, the publication of the Principia. Here's the telescope. This is finally what got him into the Royal Society in London. He sent this thing down to the Royal Society, and they were very impressed with this mathematician, kind of unknown mathematician up in Cambridge. I mean, not unknown. He did hold a chair of math in Cambridge. That's not nothing at all, but he hadn't published very much. He did some work in mathematics with some mathematicians we're aware of, but all of a sudden this telescope arrives down in London, and they were very impressed and right away invited him to become a member. And his later life, in fact, at some point he leaves the universities, he's offered a job from influential friends to come to London. First of all, works as the warden of the mint, and then actually becomes master of the mint, and was there for quite a long time being an administrator. Turns out this guy who had no friends and no social skills at all turned out to be a very, very, very good administrator, if not a cold administrator. And what I've highlighted here is that after Hooke dies, he does accept the presidency of the Royal Society and remains the president until his death. Yeah, as quite an old man. He ruled English science with an iron fist. And he did it, one way was through this, that he was science in England during this time. And nothing was done without his say-so. Just the last one down below, the next one down below, being knighted by Queen Anne, and is the first scientist to be given a knighthood. Well, that's true. He was the first scientist to be given a knighthood, but he wasn't. Queen Anne didn't knight him for his science. He was knighted for his work in the mint, for his great service to the crown as a wonderful administrator, getting the currency in shape and everything. That's actually why he was knighted, not because of his science. This is the only cool story there is about Newton's life. You should read it, about the Brackenstone curve. It's a very cool story and shows way in his retirement, after he hadn't done math and science in a long time, his powers were still there to impress. And just before we now begin to launch on the ideas of Newton and the culmination of the scientific revolution, I thought this graph might be of interest to you guys. If you've been able to watch most of the videos that I've suggested, then almost all these names are known to you, and just kind of see where these people are in their timelines and their overlap. And you can see that basically we have Kepler and Galileo in one generation, and Descartes in the next generation, and then finally Newton and Leibniz following in the next generation, more or less. Okay, so we will start on the Principia. I'll stop here, and again, an opportunity for anyone to ask a question or make a comment. Can someone say amen? Is anybody out there?
Amen.
Okay, thank you. I did know, I was talking to I don't know if all you guys disappeared on me. Okay.
All good. Interesting to see if any brilliant ideas come out of this COVID period, similar to what Newton went.
Yes. Well, no, there is one. In fact, the development of the vaccine is a miracle of science. The quickness that it was developed with the new technology that was developed right before the pandemic, and the effectiveness of the vaccine truly is an incredible story, and it's been written up in book form. I forget now the name of the biologist who did that, a woman, and her story is written, very, very effectively. I think if you Google that general thing, you'll come up with her and the book pretty quickly. So the Principia. considered the single most important work in the history of science, I'm sorry. It's in 3 books. It looks very much like Euclid's Elements. If you thumb through it, there are axioms and theorems and proofs, and that basic format of Euclid has not changed. 3 laws of motion are in the first book, and the second book deals with motion of fluids, just as Archimedes basically laid the foundation of static hydrodynamics. Hydrostatics. Newton, here in book 2, invents the science of hydrodynamics. And book 3 is the system of the world, which is the motion of the heavens. Okay. So let us go through the laws of motion. Of course, we'll need the first 2 to make the point that I want to make. The first law of motion, as stated in the Principia: every body persists in its state of being at rest or moving in a uniform, straightforward line. Uniform meaning constant speed, except insofar it is compelled to change that state by forces impressed. Okay, that's the way Newton. An object moving at a constant velocity will remain in that state unless and until it is acted upon by an unbalanced force. And our writer here, the motorcycle, is a good example of the law of inertia. The motorcycle is stopped quite dramatically, start quickly, but the rider will continue to move according to the law of inertia. Okay, he has the velocity, the speed of the bike, and he will continue to have that speed until other forces take over to change his motion. And of course, there is no force now acting on him. It's the force of gravity, right? And he will move in a projectile down to the floor, just the way Galileo showed, as we saw last week. So a new force will take over while he's moving through the air, obeying the law of inertia, continue the motion that he did have. The new force of gravity takes over and starts to move him towards the ground in an arc of the parabola, until he finally hits the ground, in which now another force will take over, the force of friction against his body, which will finally slow him down and stop him as a heap. So an example of the first law of motion. Let us define the word acceleration, because we'll be using this a lot. What do we mean by acceleration? It's not difficult. It simply means the change in velocity. But the thing we have to realize, guys, is velocity is both speed and direction. If you're changing your speed, you're undergoing an acceleration. If you're going faster and faster or slower and slower, that's an acceleration. Also, if you're turning in a curve, if you're changing your direction, that's also considered an acceleration. And what the first law says is you will move without any acceleration as long as the forces that are on you are balanced, and they could be balanced out to effectively of 0. That could be no forces or many forces in which they're all balanced. If that's the case, you will have no acceleration. You will move at a constant velocity. Your speed will not change and your direction will not change. Okay? That's the meaning of the first law. So constant velocity means that we have balanced forces. Changing velocities or acceleration, that means we have unbalanced forces. Okay? And a very good example of balanced forces giving us constant velocity is the parachute. You jump out of a plane with a parachute and you begin to accelerate. And you go faster and faster and faster until the open parachute catches enough wind of your falling down that the force of the air up against the parachute will finally equal the force of gravity pulling you down. And your net force will be 0. The forces on you will balance and you will stop accelerating. You'll hit what's called a terminal velocity, and your hope is that that terminal velocity is slow enough that it won't break your legs when you finally hit the ground. So it is not that the balanced forces creates no motion, it creates the state of constant motion, where 0 motion is one example of a constant motion. But any other constant speed in a straight line is just as good as rest. They're the same state, the state of 0 acceleration. Okay, so that's a little bit of physics 101 ram down your throat in a real hurry, but we do need this concept if I'm going to show you what I'm going to try to show you. So an example, I'm sorry, one consequence of this for our discussion going forward is, in order to move in a curve, a body must be acted upon by an unbalanced force. Otherwise, moving in a curve represents an acceleration. Therefore, there must be an unbalanced force on you. Question? Okay, someone needs to mute themselves. You're not muted. We come to the all-important second law. Force is equal to mass times acceleration. This is not the most famous equation in the world, but it is probably the most fundamental. E is equal to mc squared, I imagine, is the most famous equation, but this is where all of physics truly starts, in Newton's second law. So let me explain that. The first law, remember, is unbalanced forces, and only unbalanced forces create acceleration. Newton says that an object's acceleration is proportional to the unbalanced force impressed upon it. That's where acceleration will come, from the unbalanced forces. And in fact, the acceleration is proportional to that unbalanced force. The greater the unbalanced force, the greater acceleration you will experience. The direction of the acceleration is always in the same direction as that unbalanced force. To turn a proportion into an equation, of course, you need a constant of proportionality, and he called it the quantity of matter, and we now call it the mass of the object. And so the second law is the net force on a body creates an acceleration to the tune of mass times that acceleration. And you could look upon this really as a definition of force. What Newton has done here is he has quantified the idea of force in a very definite and essentially simple way. This is how you measure forces. You measure forces by seeing how it accelerates different masses. That's how you quantify and get your hands on what forces are. Never done before. This, finally, we have a concrete notion of force and how to measure it. And for our examples, for what we're concerned with, trying to look a little bit at circular motion, here we have, let's imagine this as we're looking at a puck on an ice surface with no friction, and we're spinning it around. We're looking down from the top as this puck goes around the frictionless ice, and we're holding the string, and we're making it go around and around in a circle. This is an acceleration. Even if it's going at a constant speed, it's still an acceleration because it's changing its direction all the time. This requires a force, and that force is the tension on the string pulling the puck in towards the center, called the centripetal force. And the quantity of that force, the strength of that force, is the mass times the velocity squared over the radius of the circle that it's moving in. This you'll have to take my word for it. The acceleration v squared over r was discovered by Huygens and independently by Newton, and they both used it to great advantage. So this is something that I'm going to ask you to accept. If the spring breaks, once the spring breaks, then we have balanced forces. The unbalanced force of the tension is now gone. We have the weight of the puck down and the push of the ice back up. Those forces are balanced. There's no friction. And what will happen? That thing will move in a straight line at a constant speed in whatever direction it had at the moment. And at any point, and moving in a circle, the direction at that instant is tangent to that circle. So when you break the string at any point, it will move off tangent to that circle at the constant speed it had at that moment. So again, for unbalanced forces, the unbalanced force here is the tension. The tension's not balanced by anything, so it creates a changing velocity. For balanced forces, we have a constant velocity. Okay, again, I'm compressing, weeks of a physics course into just a couple of slides. The acceleration being v squared over r, I ask you to accept that formula on faith. Okay, but you don't have to accept that the force involved with that acceleration of v squared over r is m v squared over r. That's Newton's second law. If you see an acceleration, the force that's creating that acceleration on that mass is the mass times that acceleration. F is equal to ma. Okay? The fundamental law of classical physics. Okay. And the third law is the action and the reaction business, which we all know, that sing-song stuff. Fortunately, we don't need this law for what we're going to do. Okay, so we come now to the system of the world. Book 3. He says in the beginning, his introduction to book 3 is, in the preceding book 1, I have laid down the principles of natural philosophy. Principles not philosophical, but mathematical. A direct swipe at Descartes. Descartes wrote a book called The Principles of Philosophy. Newton's book is The Mathematical Principles of Natural Philosophy. So these are principles not philosophical, but mathematical. But lest they should be appeared as themselves dry and barren, I've illustrated them here and there, given an account of such things as are of a more general nature, in which natural philosophy seems chiefly to be founded upon. It remains that from these same principles, by the way, the things he's shown kind of off and on and back, that's like explaining the tides and the precession of the equinox. But those are he was kind of giving examples. But what he really is interested in is book 3. It remains from those same principles, I now demonstrate the frame of the system of the world. And as Legrand said, that statement can only, if it's true, that statement can only be written once. There's only one system of the world to explain its frame of. And Newton not only was a genius, but very lucky, because he was the first one to be able to get after this problem, to explain the system of the world. And of course, what he's talking about is the motions of the heavens and tying them into what we see in motions on the earth. So what is that frame? That frame is based upon the 3 laws of motion and his law of gravity. Okay? Here is the mathematical form of the law of gravity. We have 2 masses. They will attract each other by the proportion of their product of their masses and inversely proportional to the distance between them. Okay? It's proportional to these quantities. You turn a proportion into an equation by setting a constant of proportionality, and now we have an equation. The force of gravity is this constant times the product of the 2 masses divided by the distance between the masses squared. This is the force of attraction between any 2 bodies in the universe. And we can go back to Galileo's experiment of dropping the 2 balls from the Tower of Pisa, and they fall at the same height. Okay? Galileo demonstrated this. He showed this to be the case. Whether he did or not, we don't know. But he knew that this would be the case. In fact, other people actually did do this experiment. There is documents at the same time of around Galileo, people did do this experiment to show this to be true. Why is it true? Well, what's pulling the body down? The force of gravity. There's the force law. It's G times the mass of the earth times the mass of the ball divided by the distance squared. What's the distance between the ball and the earth? It's the distance of the center of the earth. Yeah, Newton had to prove that. It's one of the great theorems that you learn when you take Calc 2 and you learn about integration. This is a very important integration to show that the mass of a central body, of a round body, a sphere, acts as if it's concentrated at the center. So the distance between a body and the earth is the distance between the body and the center of the earth, which essentially is the radius of the earth. So there's just the law of gravity applied to the body dropping from the Tower of Pisa. Well, that force of gravity creates an acceleration. We even know the value. It's G, 32 feet per second, faster every second. That's the acceleration. According to the second law, that acceleration is caused by the force of gravity. So the second law's force of mg is the same as the force of gravity. So you put them equal to each other. The force that's manifesting the acceleration is created by the force of gravity. Notice that the mass of the ball is on both sides. You can cancel them out, and you find that G is equal to capital G, which is a constant, times the mass of the Earth, which is a constant, divided by the size of the Earth squared, which is a constant. And G is a constant for all M. G is the same for everybody. And so we have the Tower of Pisa. And guys, we could do this all day. Right? We could spend 4 or 5 classes on taking Newton's laws and deriving, we just clearly don't have the time for this, okay? But I wanted to show you some simple examples of how this is done. Newton explained the idea of the satellite, okay, why a satellite can go around a central body. How does that work? This is a picture from the Principia, a very famous picture. He imagines a cannon on top of a mountain, and you shoot it off, and of course, it's going to move in a parabola. Galileo showed that. Faster, well, it'll go even further in a parabola. If you shoot it out even stronger, it'll even go further in the size of the parabola. But finally, if you shoot it fast enough, it'll go so fast that as it's turning and as it's falling, but it's given the sphere of the Earth, given the fact that the Earth is falling down, but never can reach so it is falling down. It is being pulled towards the Earth, but because of that speed, it's continuing to turn and turn and turn, just like the ice puck being turned by the tension of the string. It's exactly the same phenomenon going on, that the Earth is pulling on the cannonball, pulling it into this circular orbit. And in fact, his laws go and show further, his mathematics shows further, that depending upon the speed of the cannonball, not only could it go in a circle, but it may go into an ellipse or a different kind of an ellipse, could even go in a parabola or a hyperbola. It can go in any one of the conic sections, depending upon what energy, what initial speed you give the cannonball. Okay, this of course all assumes that there's no friction, right? And these different eccentricities and these different conic sections are shown very nicely in that Caltech video on energy and eccentricity. If you wanted to know more about this, I really recommend you watching that video. The animations are very, very nicely done. He says in the Principia, and after the same manner that a projectile by the force of gravity may be made to revolve in an orbit that go around the whole Earth, the moon also by the force of gravity may be continually drawn aside towards the Earth and would be made to revolve in the orbit it now describes. So he sees that this law of gravity is not only creating, the projectiles of Galileo, not only the apples falling from the trees, but not only the motion, of course, of the moon going around the Earth, but clearly the planets then going around the sun. It's all the same law. It's all the same force law of attraction that's creating this. And to go back to that quote that he made about his thinking about the orbit of the moon and the forces way back when he was 22 years old, back in his mom's farm, he has the acceleration of the Earth, which is, he knows, has a number of 32 in feet per second. Of course, I'll be using modern numbers. He has the acceleration here being 1 Earth radii away. He can go ahead and calculate the acceleration up at the moon being 60 Earth radii away. He knows that number, okay? It's a number that's well known. And he has this idea that the force, therefore the acceleration, should fall off at 1 over the distance squared. Therefore, the acceleration of the moon should be 32 divided by how far away the moon is compared to the 1. This is 32 over 1. This should be 32 over 60 Earth radii squared. And he compares these two numbers. He does this calculation and compares the two numbers. This is the numbers that agreed pretty nearly. But they weren't near enough for him to be satisfied back then. Turns out he didn't have a very good distance to the moon. And so he was off by a bit and was hesitant to go forward. And historians of science believe he really put this idea aside for many, many years. It turns attention to his math and to his optics and to his alchemy and all the rest. He put this aside because he couldn't quite get these numbers as close as he thought they should be. And in fact, they are very, very close when you use the proper numbers, which he had available, later on in writing the Principia. Okay.
Peter,
Question?
is it okay to ask a question now, or you want to finish what you're doing?
Let me finish these next two slides.
Sure.
And then I'll take your question.
Sure.
I want to do two pieces of mathematics besides the derivation of the acceleration here on the Earth being constant. I want to do two other derivations here. We'll take the simplification that the orbits are in circles, and this actually is his first derivation. He first of all does it using circles, and then applies his calculus to do the ellipses. We can do the circles because it requires just some algebra. I'm going to derive Kepler's third law from his law of gravity. Here are the parameters that are definitions. I remind you of the third law, that r squared over t squared is a constant for all planets. So we start with this fundamental equation here. On the one hand, we have the force of gravity. The force of gravity, we know, creates an acceleration. Any force creates an acceleration to the tune of mass times the acceleration. Here's the force of gravity with this equal sign. Here's the second law of motion with this equal sign. And here is what the acceleration is. This is that one equation I asked you to accept from me on faith, that the acceleration moving in a circle is v squared over r. If you can accept this, all I need besides these assumptions is will be, well, sorry, that's all I need. I can now derive Kepler's third law. I'll do some algebra. I'll take my speed and expand it as distance over time. This is the circumference over the period. That's all speed is distance over time. I'll expand all that out with some more algebra. I'll simplify this algebra to this algebra. Haven't changed the left side at all yet. I've got one equation equal to another. But I notice there's a mass on both sides. Just as before, I can cancel that mass out. And I can gather r cubed over t squared on one side and throw everything else on the other, right? Through the power of algebra. And look what I have on the other side. I have a constant times a constant divided by a constant. R cubed over t squared is a constant for all m, for all satellites. All the satellites of the sun will follow this law. That's Kepler's third law. Okay. Let me do the other way, going the other way, and then I'll talk about the chicken scratches of the algebra. Newton goes along in solving the Kepler problem. He goes ahead and proves that trajectories are all conic sections based upon, the energy, the initial speeds of things, just as we understand Newtonian mechanics today. Let's now go the other way, and I'll take questions. Let's now prove the law of gravity from Kepler's third law. Yeah, Newton is the one who finally understands the importance of Kepler's third law. Again, I remind you what it is. We're going to use it now to derive the gravity equation. R cubed over t squared is k. I begin exactly with the same equation, but now I know that the force, which the second law tells me in MA, the force that the planet is feeling is mv squared over r. Okay, I have this assumption. Okay. I do exactly the same algebra as before. This is exactly the same line, guys, as the other first line. I take the velocity and expand it out to be distance over time. This is exactly the same algebra. Let me do an algebraic trick. Let me multiply this mess over here by the number 1. Can't fault me for that. R over R is the number 1, doesn't change a thing. That will result in some more algebra. Okay? And by the way, your math types should follow this algebra or do it yourself. Have some fun. All this, you'll be able to verify this for yourself. I have another algebraic expression by simplifying this one, sucking it inside. I can take this expression and also isolate it, get r cubed and t squared together, and whatever is left, more algebra. But this is K. This is Kepler's third law. I'm using Kepler's third law here. This is nothing more than K, okay? I take this red and I make it K, a constant. I suck the K in and get this algebra. And the first thing that I see is that the force on the planet is equal to a constant divided by the distance squared. So I now have the form of the law that the force on a planet is inversely proportional to the distance squared. One more mathematical trick. Let me take what I have so far and multiply it by another one. The mass of the sun divided by the mass of the sun. Doesn't change a thing. Changes the algebraic form, doesn't change a thing. The force is still equal to this. I go ahead and suck those two m's in, and look what I get. I get this thing in red, where one of the masses goes this way and the other mass goes this way, again, with all legitimate algebraic manipulation. And what do I have in red? I have a constant. I have 4 pi squared, the constant of third law, and the mass of the sun. This is a constant. This is G. And what's left is the form of the law of gravity. So we have derived the law of gravity from Newton's second law and Kepler's third law. And algebra. Yeah. So let me say a word about the algebra, and then I'll take some questions. For you non-math types, I understand this looks like just a bunch of chicken scratches, and you're not impressed at all. You really quite make of what I'm doing here. You trust me that what I'm doing is correct, but it doesn't really move you. There's nothing, what is of substance going on here? Okay. You math types hopefully do know what's going on here. But let me explain for you guys who haven't done math in 50 years, okay? It's not your fault. Okay? But let me just spend a minute to explain what's going on here. What's going on here is we have certain premises. We have the second law. We have the fact that acceleration in a circle is v squared over r, another result. And we have Kepler's third law. We have 3 premises, and we're making a logical argument, very similar to the way a lawyer writes a brief. They have their facts, they have their premises, they have the rules of law, and they make an argument. They make a logical argument to reach a conclusion. That's what's going on here, guys. But the language that we're using is not the language of English. We're using the language of algebra. We're using the language of mathematics. This is just as valid a logical argument as any logical argument that you've known in any other sphere of your experience. It's foreign to you because you don't work in this language. But as Galileo said, if you want to understand nature, this is the only way to understand it. Otherwise, you wander in the darkness of a labyrinth without being able to understand and use this language. It is not chicken scratches. This is a logical argument being made, but it's being made in the symbolic form of mathematics. Okay, questions?
Did Newton, like Galileo, did all these physical experiments, the dropping the balls, inclined planes? I've never heard about Newton doing any kind of empirical experiments. Did he do that at all, or was it all math in his head?
No, of course, all the optic stuff. He did tremendous experiments with the optics, with the prisms and breaking up the light and understanding all that stuff. Tremendous stuff, experimental work there. He broke new ground in experimental attempt. He was also an alchemist. He did a lot of alchemy experiments, which didn't go anywhere, but he spent a lot of time and energy boiling things and mixing things and stuff like that. We don't know that he did very many experiments with mechanics. Really, the stuff that Galileo left him was enough of the fundamental principles. Once he had his F is equal to ma, once he could quantify the forces, what Galileo left him was really enough to begin to build his mathematical theory. That's a very, very good question. Thank you for that question. Let me move on, guys. Let me see if I can finish. We are running out of time. It's an occupational hazard of teachers to not have as much time, but just to, again, to dip into the Principia, predicting that the Earth would have a bulge because it's revolving, according to the forces that he's explaining, it would be more like an orange being squashed. This was very controversial. People didn't believe it until finally a survey was done in the 1700s that actually proved that the Earth did have this ellipsoid shape. And this is a direct verification of the rotation of the Earth. The fact that you can measure the Earth and find that it is wider in the equator than it is from North Pole to South Pole. He finally explained the precession of the equinox. This is not as complicated as it sounds. It was discovered by Hipparchus a long, long time ago, but no one had any explanation for this. And here is the Earth. Here's the axis of the Earth. Because of this bulge, the force of the attraction of the sun will cause this axis to wobble. It'll go in a very slow circle. It'll take 26,000 years to make its complete circle, wobbling back and forth. Because the axis is wobbling back and forth, here's the equator of the sun here. I'm sorry, the equator of the Earth. Just take the equator and throw it out to the celestial sphere. Think of this as a wire. And here's the ecliptic. Here's the path of the sun. Again, take that and think of that as a wire. If this thing is wobbling back and forth, then the equator is also wobbling back and forth. And as the equator wire wobbles back and forth, the place where it crosses the sun will wobble back and forth and back and forth. But where the equator, our celestial equator, crosses the ecliptic is the first day of spring. And so this is the precession of the equinox. Newton finally explained this using the law of gravity and the tides. Okay, so Newton's achievements in mechanics, not his math, not his optics, just in his mechanics. His three laws of motion and the universal law of gravitation keep satellites in their orbits, whether they're binary stars or comets or planets or moons or space probes. He explains the free fall of objects in any gravitational field, the rotation of bodies, and why bodies can either stay on a rotating body or not. Explains finally why we're not thrown off. We could actually calculate the force that's trying to throw us off the Earth compared to the force of gravity that's keeping us on the Earth. And that force that's throwing us off is a tiny, tiny percentage of the force that's keeping us on. He explains the shape of the Earth, the motion of the tides. He even calculates the mass of the moon. Okay, this is just some of what's in the Principia. And just to give an example, here is the Rosetta space probe done by the European Space Agency. This is a comet, guys. This is a comet going around the sun. And the Rosetta space probe has this incredible orbit, passes Mars, goes out, and finally catches up to the comet way out here around Jupiter. The space probe catches a speeding comet and then launches a probe of itself to land on the speeding comet and takes pictures of the comet before it finally, destructs with the. This is all done using Newton's laws. There is no general relativity here or quantum physics or anything like this. This is 19th century mathematics applied to Newton's laws that we just took a look at. Okay? There's one example of many, many that we could pick from NASA or any place in terms of what's being governed. As the great statement that Tom Hanks makes in the movie Apollo 11, when they just turn off all the engines and speed around the moon and start to come back to the Earth, he says, well, now just Isaac Newton is our pilot for a while until we try to do that last burn. It's a nice statement about Newton's laws. So Newton's legacy. He extends the methods of Galileo, to give a unified mathematical description of both celestial and terrestrial motion. This unified mathematical description is embodied in the three laws, the universal law of gravitation, in which he's able to quantify the forces for the first time to determine the motion of bodies. Gravitational force, which accounts for most of the known motions of the universe at this time, okay, is only a mathematical description. We only have that formula. Okay, there's no known agent for this. The ultimate level of explanation is limited to this mathematical description. And this ultimate level of mathematical description has determined the methodology of science since the present to the present day. This is not science according to Descartes. This is not even the ultimate story according to Newton. That one body should act upon another through a vacuum without the mediation of anything else is so great an absurdity that no man suited to do science could ever fall into it. Gravity must be caused by an agent. But whether that agent be material or immaterial, I leave to my readers. He did not know what caused gravity. Okay? In fact, in the later part of his writings, he attributes this to somehow or other to God imbuing the force of gravity in objects. He had, Newton was a very, very religious man, as was Descartes, as was Galileo, as was Kepler. These are very religious people at their time. Okay? Do not think that this paradigm that's being delivered, this very secular paradigm, was developed by a bunch of atheists. Quite the opposite. Okay? These were highly religious people. But what their science brought them, what their science showed them, the change in paradigm was inevitable. They just always had at their last resort, when nothing else could explain. They, of course, as people of their time, turned to God. And the ultimate shift in paradigm, the materialism, the mechanical philosophy, finally we have determinism, right? The ultimate shift. Within science, determinism is the claim that all processes can be fully described through a set of fundamental laws of nature, which always have a unique solution if you're given the initial conditions. The state of any configuration of a physical system is totally dependent on the mathematical laws governing that system and the parameters of the immediate prior state. And even when probabilities are involved, if those probabilities can be computed, then the equilibrium state of the system can in fact be determined. Okay? This is the fundamental determinism of classical physics. Okay? What we do with Heisenberg's uncertainty principle, etc. Yeah, that's the paradigm shift. Okay, but this is what the scientific revolution has left us with. Materialism, that the only thing in the universe to be contended with is the mass of bodies and how they move. They are governed by the laws of nature, only by the laws of nature. And the laws of nature are mathematical in nature. And in fact, what's left, all that's left in terms of our explanations is nothing but the equations. There is nothing else. All we have is the descriptions, the mathematical descriptions that we see in nature. Oh, it's very powerful descriptions. They can make wonderful predictions, and those predictions seem like an explanation, but when you look at them at base, all we truly have is a mathematical description of what we can see in the widest sense of the word see. And given all of that, given that mathematical description, since it's math, everything is determined. Everything would be known if we knew all the initial conditions and we knew all the mathematical laws, which we know are there, whether we know them or not, whether we have statistical laws or true equation laws. If we could ever know them all, we would know everything. We would know how the universe would unfold. This is the fundamental paradigm shift. You can't get any further away from the classical Christian paradigm that was overturned. This paradigm, of course, is one that we still live with. We still have a vague understanding that this makes sense to us on some level. This is what we see around us. This is how we interpret what we learned about science and about the world. And we are struggling to try to understand the new paradigm shift of the quantum revolution. Not relativity, by the way, guys. Relativity, both general and special relativity, are classical theories. They are completely deterministic differential equation, Riemannian geometry-based classical theories. It is the quantum theory. It is the wave-particle duality. It is the entanglement. It is the Heisenberg uncertainty principle. It is those principles which throw this paradigm into total chaos, which we are still trying to struggle with. And I'm sorry that we have run out of time, as I knew we would. I apologize. I wish we had one more class, but we don't, to talk about the paradigm shift here that we just studied compared to the one that we're living through. But that's my course. That's our story. Any questions or comments before we go?
Only just loved the course, thought it was really interesting, loved the way you described things and showed us what was going on. I really enjoyed it a lot. Thank you so much.
Thank you. Appreciate that. Any thoughts, any questions about what we talked about today? Observations?
I've always been wondered about the force having to do with the distance squared between the two bodies. Newton obviously didn't verify that by experimentation, but can you say any kind of word to enlighten?
No, he did. He did. He was able to show that the acceleration of the moon really did fall off compared to the acceleration of the Earth of that 32. He eventually was able to show that that acceleration was 1/60 squared of the acceleration of the 32. He did verify at least that.
Did he do that by observation?
Yes, he got his numbers from Flamsteed, the Astronomer Royal, of just how far away the moon exactly was, and he did the calculation and showed that it actually lined up very, very well. But of course, his ultimate justification is his derivation of all three laws of Kepler. Can you imagine the accomplishment of that? He takes his laws of gravity and his law of motion and derives in turn each one of these independent laws of Kepler, which of course leads to the accuracy of the solar system. And then he goes the other way. He takes the three laws of Kepler and uses calculus and with his law of motion, F is equal to ma, and derives truly in an exact way the law of gravity. He goes back and this is an incredible tour de force, which is what the professor at Caltech talks about. That legacy, something he says, you students can now own. You can own that derivation. It's like the Sistine Chapel. It's like the Beethoven's symphonies. It's a piece of our Western heritage of what Newton is able to do, going back and forth between the laws of Kepler and its consequences and his mathematical theory. It is breathtaking. And when you get a chance to learn this, generally you learn this in sophomore year, your intermediate mechanics course, it is truly monumental as a student to finally see how this is done. It's not done the way Newton does it. It's done using modern calculus and vector calculus, but that's not important. The math that's used is not important. The fact that these systems can be brought together under one mathematical law is just breathtaking.
But can you say?
Okay, if I've left you breathless, why don't we end it there, guys? I don't like to keep you. So it's been great. You guys have been great. I loved your questions. I loved your attention. I really, really enjoyed teaching this course. Very much so. Very, very much so. So thank you for that. All right.
You come back in the fall, Peter, with another course on quantum mechanics, or
Okay.
yeah.
I'll let you know.
All right.
All right, guys.
Thank
Very
you so
good. Be
much.
good. Have a good summer.
Thank you.
Thank you.
Bye-bye.